Okay, so the title of the series is the geometry of uh, random geodesics. Um, it's not that general. It's a little pompous sounding, but uh, I'm eventually going to talk about Busemann functions, and the title is sort of inspired by that. So essentially, I'm just going to approach this problem almost entirely through this model called first passage percolation. And first passage percolation is sort of a canonical example of a metric, a random metric on a lattice. Okay, so let me describe um, the model. Okay? So let me tell you my plan as well. My first two lectures are going to be completely expository. I'm just going to introduce you to this model, talk about why it's interesting, and do some basic setup. And maybe in my third talk, I'll advertise a few of my results, but it's mostly expository. So there will be some repetition if you attended my talks at ISI a couple of weeks ago, but the overlap will only last about half an hour, I would say. And once we get to start it, once we start talking about geodesics, it'll be completely disjoint. Okay. So first passage percolation is a model for random growth. So let me show you a video. 1 second, while I set it up. Okay. So what it's showing you is a sort of idealized droplet of fluid sort of exploring a random medium. Okay? So this random medium has some holes, and this fluid is going at different rates through these different holes. So it's a porous medium, and you sort of want to describe the behavior of this process. Okay? So that was the original motivation. It might seem like an extremely boring problem, but it has incredible connections to all sorts of areas of mathematics, including representation theory and number theory and so on. So let me describe this model a little bit more. 1 second. A little bit more mathematically. Okay. So. Sorry, it's a bit messy managing so many screens. Let me try again. Okay, so the description of the model is you can do it on many different spaces, but classically it was always described on the lattice. Okay? So basically, you say I'll give you a field of IID random variables on the edges of ZD, and these sort of represent the time for a fluid particle to cross the edge, to cross. So suppose I want to get from say this point, which is x, to that point, which is y. The fluid could take, say, this particular path from x to y, these particular edges. And so then I'll say that the weight of this path, sorry, why is it not going to black? Just give me 1 second. So the weight of this path, let me call it gamma. That is just the sum of the edges in gamma of the weights it encounters. Okay, so that's the weight of this path. Of course, I'm interested in a quantity called the first passage time, which is the infimum over all paths from x to y, I'll use this notation, of the weight of each path. So it's the first time for the fluid, it's the first time that a droplet of fluid released at x would reach the point y. Okay? So that's my simplistic description of this percolation phenomenon, and this is my precise mathematical model. So usually I will just write t of x when my first point is the origin, and I'll extend t to be a function on Rd by saying t of x equals t of these things, and this means nearest lattice point. Okay? And so now it's a function, t is a map from Rd. Okay? R plus is non-negative real numbers. Okay. Any questions so far? Is that a fairly straightforward description of the model? I have some fluid, I have some random weights, and
it doesn't have to be a geodesic, right? Any path, as you showed in the picture.
that's just if I fix any path, this is the time it takes for the fluid to go from x to y. You just sum the weights because that's how long.
All paths.
I take an infimum over all paths. Okay, so I should say that these are generally non-negative, otherwise the model wouldn't make too much sense. If they're allowed to take negative values, then this first passage time could be minus infinity.
So far there is no probability.
Only in the
But this is for any fixed realization.
any fixed realization so far. So okay, so there are various versions of this models. You can have vertex weights instead of edge weights. You can think of more complicated lattices and so on, but all of that's not that interesting. So the set we saw in the video was the set of points x in Rd such that the passage time to x is smaller than or equal to t, and t was evolving, t was increasing. And so we're loosely sort of interested in the limiting behavior of the set. That is, in some sense, what happens as limit t goes to infinity of b of t. Of course, you saw that it's increasing. If we want to speak about it mathematically in some way, we had better divide by t, and this turns out to be the right scale or right rate of growth. Question. Okay, so seems to be a fairly complicated phenomenon, but you also saw that a sort of
It's a set, right?
It's a set. I'm not being precise. I'll be precise in a minute. It was sort of clear that there was some average rate of growth. So that would be my first asymptotic for the set. Okay, so I have a big set. It grows at rate t, and so maybe this is bt. There are some random fluctuations, but really I want to describe the shape, the limiting shape of this process. Okay, meaning, is this limit, for example, a circle? So here's an argument as to why it should be a circle. You take two random walks, IID random walks, okay, and whatever bounded weights or whatever, and or in fact you may even let this random walk be plus or minus one, Bernoulli one, random walks, one in each coordinate, and I'm looking at the endpoint of this random walk at time n. Okay, so let's say Sn is this random walk. Has two coordinates, xn, yn. Xn, yn are Bernoulli random walks. Bernoulli random walks, and they take values in in plus or minus 1. So assuming plus 1 and minus 1 are, are equally likely, then by central limit theorem, this goes to a Gaussian. Okay, I'll just write it like this, and again I'm being a little loose, but I'm assuming you know what I mean. 2 pi. Hope I got the normalization right. I think that's right. So now you see that somehow in this limiting behavior, I get this circular symmetry. So I took a process that sits on the lattice, meaning I'm going plus one step at each point in time, and after n steps, somehow when I zoom out and look at this process, I see a circle. So it has forgotten the structure of the lattice. So basically, I've taken some process on the lattice, added a little randomness, it's become a circle. Okay, so question is, do we expect the same thing here? So I'm always curious, how many of you think it will be a circle? Is convincing enough argument? Not too many. You guys are smart. You realize that I'm trying to mislead you. So let me show you another couple of videos. So let me describe the distribution that I used. So when I showed you this video, one second. When I showed you this video, sort of the limiting behavior seemed to be that it looks a lot like a circle if I zoom out, right? But let me show you another video. Okay, so what I didn't tell you was the set of weights I use. So I used TE being uniformly distributed between 0 and 1. So basically, I have a uniform density. This would be its PDF. Now let me change these weights a little bit and say, okay, so how about I just make, maybe I'll support these on 1 and 2, just to avoid 0 because 0 is a little weird. And so suppose I say it's distributed as follows, and I'll draw a picture of its PDF. So that's a big mass on the point 1, and between 1.8 and 2, it's uniformly distributed. Okay, so this has the probability that tau E equals 1 is bigger than 0. It's large enough in some sense, and I'll mention what large enough means in a second. Okay, so let me show you this video.
So you said it has a mass at 1?
It has a mass at 1. Okay. Okay, so now let's see what happens to the shape. Now it clearly becomes a diamond. Okay, so diamond with soft rounded edges.
One question.
Yeah.
I think you mean symmetric distribution because you have to go on the other side as well. You said distribution is between 1 and 2. Did you symmetrize it to go on the negative side as well, on the lattice?
No, I didn't.
Is it positive random variable?
Positive random variables. Yeah.
Otherwise, it cannot be well defined.
It might be, you could find a big negative path and sit on it for a long time, it could run off to infinity.
So
You can
ZDs are all positive.
Huh?
ZDs are positive. the random variables on the edges are all positive.
Are all positive.
So the question was whether it will always be a circle, is it?
Yes.
Okay.
And clearly it won't.
So if it has a density, then one expects something nice.
Yeah, but here I think it is the mean which is being wrong. Okay, maybe my intuition is wrong, but it looks like whether you go on the x or the y, you are having some constant movement. That is that conserves the x plus y in some sense. So there is an L1.
That's right. It is definitely a perturbation of the L1 metric, because suppose in the trivial case you could have a random variable supported on just one, on the weight 1. Then it would certainly be an L1 ball. And you can see.
Arjun's question that whether there is some distribution for which it will be a ball or something.
No, if it's absolutely continuous.
Is it a ball always? I don't think it's true. For example, in this weight, let me show you. I've superimposed a circle on this growth. So.
Do you expect any continuity in terms of the distribution mapping onto the shape?
Continuity in what sense?
Say which star in the space of metals on the say interval 0, 1, and this shape is compact, so we get no more loss of topology or something like that.
So you're asking if a series of sequence of distributions Fn converge to F, does the time constant or the shape converge in some sense, in some appropriate sense? Yes, that's true. I'll state that theorem.
In that sense, the absolute continuity follows, because if you just take a small ball around your delta neighborhood and you shrink it down, then at some point you should start looking like the L1 ball.
Yes, yes. At some point you will look at the end. L1 ball. Yes, sure.
I have a question related to this. The audio is muted on yours also. Right?
Is it?
Can you hear if someone speaks? Will it be audible there?
It should be.
It's audible. Fine. Otherwise,
I mean, we can test it by having someone speak. Can someone say something?
No, it is audible. It is audible very well. It is audible.
It's audible. Okay. 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 So now it's clear that the shape is dependent on, strongly dependent on the lattice and on the edge weights. Lattice I've not demonstrated, but it does depend on the lattice itself in some sense. Sorry?
You were showing the superimposition.
Oh, I sorry. Yeah. Okay. So here you can see that the circle superimposed on this, I did some sort of best fit, and it's not a circle.
But is it still that there is a symmetry? I mean, that symmetry could still be there without it not being a circle.
In what do you mean symmetry?
I mean, x squared plus y squared. And symmetry is preserved in the limiting market. That's still possible. It may not be a circle. I mean, it could be a curve like x. X to the fourth is 5.
X to the fourth, yeah, that's sure. You mean some, it could be some LP ball, for example.
Yeah.
Could be, unknown. Yeah. So, is it an LP ball for some LP? For some P? It's unknown. Okay. So some basic properties are known. For example, oops. No. Okay. So let's write down some basic properties. So if F0 let's say f is the CDF, the cumulative distribution function of tau e. And suppose let's avoid like uh, trivial behavior by saying f0 equals 0. You always need some time to cross an edge, which seems reasonable. Then you can show quite easily as an exercise that t xy is a metric, almost sure. One is txx equals 0, and you can write t xy smaller than or equal to t xz plus t dx. Okay, so this triangle inequality is quite easy to see. That's because I'm looking at the shortest time.
zy, right? Now this.
Yes, yes, yes. So I'm looking for the shortest time to go from x to y, and if I instead force it to go through this point z, then the time to go from x to z plus z to y is the time to go from x it will be larger than the time to go from x to y because I'm forcing it to go through z.
So xy is a metric, it's not even almost everywhere, it's always true. Once you give me a sample of the process, then it's automatically.
Yeah.
If tau is of 0, it's
Sure,
non-negative.
sure. Yeah.
You could have some density at zero, whatever. Okay. So the questions I'll be interested in, or the questions you generally ask, how does dt behave? And two, how do the geodesics of this random metric behave? Of this metric behave. So there's these two things are connected when you talk about infinite geodesics, which is what I'm most interested in. Okay. So, and of course in this, I'll focus on this, but to even begin talking about geodesics, I need to talk a little bit about how this thing behaves, this object behaves.
Sorry, can I ask a very question?
Yeah.
So, it seems that unless things are very, very funny, these first passage geodesics should look like last passage geodesics.
More or
Is there
less.
some general intuition that this problem should be related to last passage?
No, I think if I had to throw around terms, it would be KPZ universality, but who knows what that means.
For first passage.
For first passage, yeah, it is in the KPZ class. So
Okay, but I mean the geodesics themselves, should they look like?
yes, in terms of scaling, yes, but they can be longer than last passage and so on.
Yeah, no, I know in principle they can be, but you know when you take the limit and so on, should they?
Yes, yeah. In terms of scaling, yeah, for sure. Okay, so to answer this first question, it turns out it's just equivalent to describe the asymptotics of t 0 x x goes to. Okay, so this triangle inequality gives us a gives us a property called sub-additivity. Sub-additivity uh, in directions, in any fixed direction. So if, for example, I fix x in, say, the unit ball or unit circle, and um, and look at t, say nx, the time to go from the origin to nx as a sequence, then this then I'm look. Let me see how to explain this. Then we see that t nx, I'll just drop this reference to this origin and say t n plus mx for two integers n and m should be smaller than or equal to, no, let me write it this way actually. T 0 n plus mx should be smaller than or equal to t 0 nx plus t nx to n plus m. So now if I take expectation like this, I average it, I integrate over the probability measure, then I'll just get some numbers. A n plus m, a 0 comma n plus m is smaller than or equal to a 0 n plus a n plus m. I've thrown away x, but I don't care about it. But I make this short observation that because I have IID weights, this has to be the same as the quantity expectation T0 mx. Translation invariance. Translation invariance of the measure of weights gives this. So instead, I could just write this as a n plus m less than or equal to a n plus a n. And so such a sequence is called subadditive. And something called Fekkerter's lemma says limit n going to infinity, an over n exists, and in fact is equal to the infimum over an. So this Fekkerter's lemma is something very simple. And you can prove it as an exercise in 10 minutes. Exercise. And so, using this idea, turns out that just translating this, that expectation T, or rather, with a little work, with some work, you can show convergence in measure. Show theorem, Hammersley and Welsh, 1964, when the model was introduced, that T0 nx divided by n converges to mu of x for every x.
For this, you just need stationarity of the vector field.
Stationarity of the weights.
And maybe L1
and some moment. So they showed this, not almost surely, but they showed it in measure, in probability. Okay? And they assumed quite a lot of things, but assumed, say, strong moment assumptions. About the weights.
Can't you use summary ergodic theorem here?
You can, but in fact, so that will be my next point. Okay. So,
Just one comment
yeah.
on the question. So if I look at it, realization by realization,
Mhm.
there is subjectivity there as well. So why can't you apply FK and get the convergence? Is this saying something more about the mu?
That was about me, right?
So I'll answer this
You
question.
mean that the T doesn't.
So if I go
T
back,
by itself is not subjective?
T by itself satisfies the triangle inequality, but I don't get a. I'll get a two parameter subadditive sequence here. You see, there's, I don't get direct subadditive in the sense that I don't get T0 n plus mx is smaller than or equal to T0 nx plus T0 mx. I get some sort of shifted, but averaging and using stationarity, I can say that this is the same in distribution as T0 mx, and so the expectations are the same. So I'll get a sync.
The shifting is only gives you in log.
Yes.
Mu x can be 0 also.
Mu x can be 0. In fact, I'll tell you when it's not in a second. So, as Parthanel said, this theorem can be upgraded. So, I should tell you a little bit about the history of this model before I go forward. So, in fact, Hammersley and Wells introduced this model.
I have a slight doubt about the statement given there. Maybe it doesn't matter, you are giving a more powerful one, but here improbability means what? For a fixed x, you are saying.
Yeah, you're right. You're right. When I wrote it, I knew I was making a mistake, but I should say for any fixed x.
I think the strongest statement about
It needs more assumptions. Yes. Yeah.
if you just take x in S1, then you can prove under moment conditions that it's in fact continuous, and so you can prove it on a dense set of rationals and then upgrade it.
Actually, there's some more to it in the sense. Now, when you do it on a dense set, do you converge for all x simultaneously? Is another question. So
There is an issue, but it can be. I think it can be done.
that itself is one of the theorems that I was stating. So it's. Okay. So Hammersley and Wells introduced this model in 1964, and they also introduced classical percolation, sort of standard model for, I think, a few years earlier, maybe in the 50s, but I won't state when. And this Hammersley was an interesting character. He actually doesn't have a PhD, so he was later awarded an honorary PhD from Cambridge for his work in percolation theory. Okay. So this theorem can be upgraded, and this is due to Keston in the 80s. Actually, it was due to Kingman, and Keston gave the first passage version. So Kingman, in fact, proved his theorem for first passage percolation. The subadditive ergodic theorem was proved by Kingman for this particular model, and now it finds use in everything. And then I should also mention Keston's. So it says, assume some moment condition, expectation min tau 1 through tau d less than infinity, d bigger than or equal to 2. So these are d IID copies of my weights. Then there exists mu e1 in 0 infinity such that limit n going to infinity of t0 and e1, I should just say x for each fixed x divided by n goes to mu of x in L1 and almost sure. Okay. So this condition just says that if I look at some sort of reachability criterion for a point, then I need to be able to reach a point in some way, and so this is the reachability criterion. Because if all the weights getting to a point are high, then I won't be able to reach that point. So this is some sort of this minimum of the d weight surrounding a point is some sort of reachability thing. Being finite is some sort of reachability.
This D is the dimension.
This d is the dimension. Yes.
Arjun?
Yeah.
I want to know this now.
Oh, sorry. Okay. Okay.
I'm still someone in this day and age who takes notes.
I think it should be 2D actually. What did I write? D. Okay. Okay. So it should be 2D. I'm sorry.
Going to distance 1, so, right? The time to go 1 unit distance.
This is the time to go to 1 unit distance. So if I want to go from here to here, then I have essentially d ways to get to it. Okay, yeah. So I think it should 2D ways to get to it. So it should be 2D. But let me double check. Unless I. Yeah, it should be 2D.
In your model, you could have different weight for different directions.
You could. In principle, you could. But that complicates it even further, and the problem is complicated as it is. So, Keston also proved a remarkable theorem, I think, that if f0 is smaller than pc, which is the critical probability for percolation, I'll explain this in a second. Percolation. Then, in fact, mu of x is bigger than 0 for any x not equal to 0. Okay. So here I had said that it could be in 0, infinity, and now this says that it's in fact some positive number, and so my problem is non-trivial. So this proof is quite beautiful, and it uses something called the BK inequality named for Keston, Berg and Keston. Okay. BK inequality and the fact that at subcritical percolation the expected cluster size is finite, but I won't harp on that.
But now this is edge percolation, bond percolation.
This is bond percolation. Yes. So, however, I just thought I'd state these two little theorems, and I should say, however, little else is known. Is known about them. And now,
So in the previous page,
yeah.
There was some efforts to get a Boltzmann equation somewhere.
Yeah.
Yeah, what was the equation?
So F is the CDF
The CDF.
of tau, and tau is supported in 0 infinity, But it could have an atom at 0. And it's saying you can have an atom at 0, but as long as it's not too big, your time constant will be reasonably well defined. Okay. So now I want to tell you why we should care about this model. Why we should care seems to be, why do you care about this model? But before I tell you that, let me tell you about the solvable case that Arjun was asking me about. So there's one very, very special case. And this special case is a special case of edge weights in something called last passage percolation. So last passage percolation, again, I have a field of weights tau E in edges, and they're positive. And if I fix a path if I fix 2 points x and y, to go from x to y, I'm only allowed to go up and right, whatever that means in d dimensions. Then I also say, oh no, I've run into this problem before. Oh, nice. I think maybe this will work better. So, I should say that the passage time from x to y is now a max over upright gamma from x to y of the weight each one. And now, if I set my weights to be exponential 1, but exponential lambda works, of course, or is geometric p, then the limit g0 and x defined the same way is called g of x, and in d equals 2, g of x comma y is the square root of x plus the square root of y, the whole square. So it is a p-norm in this very, very special case. P-norm, well, it's not a norm, so it should see p in this special case. So the original proof was in the early 80s due to Rost, who used a sort of hydrodynamic limit approach. But since then, there have been many proofs of this fact, and let me just look up the history. Yeah, you can also compute this because of a connection to, I can never get the number of S's and N's right in his name, and so this is using some asymptotic rep theory. I think it's fair to say that. And more recent approaches use a connection to queuing. Queuing and work property. So this is where all these miraculous connections have been established rigorously. In all other cases, they are supposed to be related using some principle called universality to these models, to these results in this very, very special case. But of course, all of that is open. Okay. I should also say that the idea they use here, this Burke property they use, that actually in fact goes back to an old paper of Alderson Lycones. Okay, so Johansson also proved something even more incredible. Yeah.
At some point we can take it.
Yeah, let's do it. I've been talking.
If you want to finish something, then we go and
Let me. No, I think this is a good place to stop.
So, Arjun, in that case, can you just flash the capital G again?
Sure.
So the shape is it for the exponential, or you're saying for all geometry it is the same shape, is it?
No, it's not. I'm lying a little bit. So I should say, if I were to be honest, I would have to write it like this: mu x plus y plus 2 sigma square root of xy, and then this mu and sigma will be functions of p for geometric. But for exponential 1, this is the right. Mu is 1, sigma is 1. That's all.
So, what does G basically indicate? It's sort of the largest time, right?
It is the largest time,
Right.
the last passage time. And so somehow it being the last passage time in this particular model brings in these connections to all these different fields where you have more tools, like that's where the representation theory and the queuing comes in and so on.
This is the first place where you brought in last passage. I think then you were doing it.
I was doing first passage.
First passage.
In first passage, it's a bona fide metric, and here the triangle inequality goes the wrong way, and so.
And so, what sort of representation theory are you referring to?
Just representation theory of the symmetric group.
Ah, okay.
And in this particular case, I guess polynomial representations of the general.
One more question. You said, however, little else is known in the first passage case itself.
In the first passage case.
And then you said exactly from the stem, thrown up to the place where you said exactly from the however, little else is known. And then you went to the solvable case and then changed the last passage.
I changed the last passage percolation and said, in the solvable case for these very, very particular weights, the limit shape is known, and this is because of this remarkable connection.
But I have a question of possible solvable cases for first passage percolation.
It's a great question. I asked this question to Arvind 2 weeks ago, and there's this general principle in physics called the Yang-Baxter equations, and I don't know what they are, but if your weights and your model together satisfy them, then there's some chance of solvability, is my understanding.
Chance of solvability, or they are solved? Even that we know.
I don't know that, but somebody who knows more about the Yang-Baxter equation.
Okay, maybe we can break now. For those who are online, we are taking a break for 8 minutes. We'll meet back at 3.
We'll keep this on, right?